Hello there, and welcome back to the Science Sleepy Minds, that cosy little corner of the universe where we turn impossibly vast cosmic questions into the gentlest of bedtime stories. Tonight, you find yourself standing barefoot on cool grass, head tilted back, neck already protesting just a little as your eyes adjust to the darkness above. The city lights have faded behind you. Maybe you drove out here. Maybe you simply imagined yourself away. And now there's nothing between you and the sky but a few wispy clouds drifting lazily toward the horizon. And there it is. That faint, ghostly river of light stretching from one edge of the darkness to the other. A smear of luminescence so subtle, you almost wonder if your eyes are playing tricks. They're not. That pale band is the Milky Way. And tonight, we're going to discover just how monumentally, almost absurdly enormous it truly is. Fair warning, your sense of cosmic significance probably won't survive this journey intact. But that's okay. There's something strangely comforting about being small. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop a comment telling me where you're watching from and what time it is there. I love knowing that someone in Tokyo and someone in Toronto might be falling asleep to the same words, separated by thousands of miles but united under the same galaxy. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're still standing there on that grass, and the dew is beginning to settle on your toes, cold and refreshing in a way that grounds you to this small planet, even as your mind prepares to leave it far behind. The Milky Way above you looks so still, so permanent, like someone painted it there with a dry brush dipped in the palest silver. But here's the thing you probably don't think about when you're admiring that view. You're not looking at something distant and separate from yourself. You're inside it, right now. You're standing on a tiny rocky world, orbiting an unremarkable yellow star located in one of the galaxy's minor spiral arms, and when you look up at that band of light, you're essentially looking at your own cosmic neighbourhood from the inside. It's a bit like standing in the middle of a forest and trying to figure out what the whole forest looks like from above. You see trees in every direction, but the overall shape, that's trickier. For most of human history, people had no idea what they were looking at. That smudge of light was a mystery, a canvas onto which every culture projected its own stories and fears and hopes. Some thought it was a road for the dead. Others believed it was milk spilled by a goddess, or the seam where two halves of the sky had been stitched together. Nobody could have imagined that it was made of stars, hundreds of billions of them. Suns like our own, many larger, many smaller, some already dead and cold, others not yet born in clouds of gas and dust that won't collapse for another million years. The scale is so far beyond everyday experience that your brain essentially throws up its hands and files the information under too big to process. Come back later. But we're going to process it anyway, you and I, slowly and gently, over the course of this quiet evening together. We'll start with what ancient eyes saw and what ancient minds believed, then trace the story forward through telescopes and photography and radio waves and mathematics, until we arrive at the modern understanding of just how staggeringly, almost comically large the Milky Way really is. And then, because that's still not humbling enough, we'll zoom out further. We'll see our galaxy as one member of a small group of galaxies, which itself belongs to a larger cluster, which itself is just a tiny thread in a cosmic web of filaments and voids stretching across distances so immense that light itself, the fastest thing in the universe, takes billions of years to cross them. By the end, you'll understand why astronomers sometimes get a faraway look in their eyes when they talk about this stuff. It's not just the numbers, it's the feeling of standing at the edge of comprehension and peering into something that doesn't care whether you understand it or not. The universe simply is, in all its terrible and beautiful vastness, and you're part of it whether you signed up for that or not. But right now, none of that matters. Right now, you're just a person on a patch of grass, feeling the cool night air settle around you like a blanket. listening to the distant chirp of crickets, or maybe the hum of a highway, or maybe nothing at all except your own breathing. The Milky Way glows above you, patient and ancient, the same view that your ancestors saw 100,000 years ago when they first looked up and wondered. Scientists still argue about exactly when humans developed the cognitive capacity for that kind of wonder. Was it gradual, or did something suddenly click in our neural architecture? But the wondering itself is undeniable. We are a species that looks up. And here's a quirky little fact to tuck away as we begin. The term galaxy itself comes from the Greek word galaxias, meaning milky. So when we say Milky Way galaxy, we're essentially saying Milky Way, Milky Way. It's redundant, a bit silly, the kind of linguistic fossil that reveals how thoroughly our ancestors' mythology has seeped into our scientific vocabulary. Even now, with all our instruments and equations, we can't quite escape the poetry of milk spilled across the heavens. So settle in. Let your shoulders drop. Unclench your jaw if you've been holding tension there. You probably have. Most people do. The story of our galaxy is long and winding and full of surprises, but there's no rush. The stars will still be there tomorrow night, and the night after, and for billions of nights to come. Tonight, we simply begin. We start with eyes looking up, with minds reaching out, with a very human impulse to make sense of the light scattered across the darkness above. The grass beneath you hasn't changed, but in your mind's eye you're drifting backward now, through centuries and then millennia, watching the human story rewind like an old film reel. Cities shrink, then vanish. Roads become footpaths, become deer trails, become nothing at all. The constellations shift subtly. Polaris wasn't always the North Star, you know, and won't be forever. But that band of light remains constant, a fixture in every night sky that humans have ever observed. And oh, how they observed it. In ancient Mesopotamia, some 4,000 years ago, the people living between the Tigris and Euphrates rivers called it the River of the Divine Lady, imagining it as a celestial stream flowing through the heavens. For them, the sky was a dome, a great overturned bowl separating the waters above from the waters below, and that luminous streak was evidence that even the gods needed waterways. They weren't being foolish. They were being human, doing exactly what humans do, looking at something incomprehensible and reaching for the nearest familiar concept to explain it. Rivers, they understood. Rivers meant life, agriculture, trade, survival. A river in the sky made a kind of intuitive sense. Halfway across the world, the ancient Chinese had a different but related idea. To them, the Milky Way was the Silver River, and it featured prominently in one of the most enduring love stories in their cultural tradition. You might have heard some version of it, the tale of the weaver girl and the cowherd, two lovers separated by the celestial river, allowed to meet only once a year when magpies form a bridge across the sky. Historians still argue whether this story originated as an explanation for the Milky Way's appearance, or whether the astronomical feature was later incorporated into a pre-existing myth. But either way, the marriage of observation and narrative is unmistakable. The sky was not just something to look at, it was something to tell stories about. The Greeks, never ones to let a good myth go untold, gave us the name that stuck. Their story goes something like this. Heracles, if you prefer the Roman version, was the illegitimate son of Zeus and a mortal woman, which meant he lacked the full immortality of the gods. Zeus, being Zeus, decided to fix this by sneaking the infant to his sleeping wife Hera and letting the baby nurse from her divine breast. Hera woke up, was understandably startled to find a strange baby attached to her, and pushed him away. The milk that sprayed across the heavens became the Galaxias Kyklos, the Milky Circle, which eventually shortened to just Galaxy. It's a wonderfully absurd origin story, full of the casual chaos that characterizes Greek mythology, and it stuck so thoroughly that we're still using the word today. But not every culture saw milk. The ancient Egyptians, practical as always, associated the band of light with the Nile, Another river, because rivers were the source of everything good in their world too. Some indigenous Australian cultures saw it not as a river, but as a smoke trail, or as a pathway that spirits travelled upon after death. The Khoisan people of southern Africa have stories about it being the embers of ancient fires. In Finnish mythology, it was Linnunrata, the path of the birds, the route that migratory birds followed to reach a warm land beyond the visible world. Each interpretation tells you as much about the culture as it does about the sky. And here's something that might surprise you. Many ancient peoples actually saw darkness within the Milky Way rather than just the light. The Inca, for instance, recognised constellations formed by the dark patches, the interstellar dust clouds that block light from the stars behind them. They saw a llama, a serpent, a fox, a toad. While European astronomers focused on connecting bright stars into patterns, Andean skywatchers were finding meaning in the absence of light. It's a reminder that observation is never purely objective. What you see depends enormously on what you've been taught to look for. You shift your weight slightly, and the grass rustles beneath you. A mosquito whines somewhere near your ear, but you're too deep in thought to really notice it. You're thinking about all those people, across all those centuries, lying on their backs just like you are now, staring up at the same band of light and making up stories to explain it. They didn't have telescopes, they didn't have spectrographs or radio dishes or space probes. They had their eyes, their imaginations, and an overwhelming human need to understand their place in the cosmos. And you know what? They weren't entirely wrong. The Milky Way is a kind of river, a river of stars flowing in a vast gravitational current around a central point they couldn't see. It is a pathway in a sense. Photons have been travelling along it for millions of years to reach your retinas tonight. The metaphors weren't accurate in a scientific sense, but they captured something true about the nature of the thing. The scholarly debate about ancient astronomical knowledge runs deeper than you might expect. Some researchers argue that certain megalithic structures, Stonehenge, Newgrange, the pyramids, were deliberately aligned with the Milky Way's position at certain times of year. Others dismiss this as overinterpretation, pattern matching by modern minds eager to find sophistication in ancient works. The truth probably lies somewhere in between. Ancient peoples were certainly sophisticated observers of the sky. Their survival often depended on it, but they didn't have the conceptual framework to understand what the Milky Way actually was. To them, it was simply part of the furniture of the universe, eternal and unchanging, a feature as natural and unexplained as thunder or the tides. And then, one night in 1610, a man in Italy pointed a new kind of instrument at that familiar band of light, and everything changed forever. The mosquito has given up on you, apparently, or maybe you've just stopped noticing it. Your breathing has settled into a slower rhythm, and the night feels deeper somehow, the stars sharper against the black. But we're not quite in the present anymore. We're in Padua, in the Republic of Venice, in the early winter of 1610, and you're about to witness one of the most quietly revolutionary moments in human history. Galileo Galilei was not, despite what you might have learned in school, the inventor of the telescope. That honour belongs to a Dutch spectacle maker named Hans Lippershey, who filed a patent for the device in 1608. But Galileo was the one who took this curious toy, useful for spotting distant ships, entertaining children, not much else, and turned it toward the sky. And when he did, the universe revealed itself to be stranger and more crowded than anyone had ever imagined. Picture him there in his study, this middle-aged Italian professor with a sharp mind and a sharper tongue, peering through a tube of wood and glass at a section of that milky band his ancestors had named for Hera's breast milk. What he saw made him catch his breath. The smooth, luminous cloud resolved into individual points of light. Stars. Countless stars, far more than he could count, packed so tightly together that they blurred into that familiar glow when seen with the naked eye. He wrote about this discovery in his Sidereus Nuncius, The Starry Messenger, published later that year. The galaxy is nothing else but a mass of innumerable stars planted together in clusters. Nothing else but. Listen to how casual that phrasing sounds, as if Galileo didn't fully realise he had just overturned thousands of years of mythology in a single sentence. The Milky Way wasn't milk, wasn't smoke, wasn't a river or a pathway or a celestial scratch. It was stars. Just stars. The same kind of objects as those brighter points scattered elsewhere across the sky, only much, much farther away, and therefore much, much fainter. This was radical. Dangerous even in ways Galileo would come to understand personally when the Inquisition later forced him to recant his support for the heliocentric model of the solar system. But in that winter of 1610, he was simply a man looking through a tube and seeing something no human had ever seen before. The universe had suddenly grown vastly larger and more populous. If the Milky Way was made of stars, how many stars were there? Thousands? Millions? The telescope couldn't tell him, not precisely, but it was enough to make the question urgent in a way it had never been before. And here's a quirky detail that often gets left out of the triumphant retellings. Galileo's telescope was terrible by modern standards. It had a magnification of about 20 times. Your average pair of binoculars today is better. And the images it produced were blurry, distorted around the edges, prone to chromatic aberration that created false colours around bright objects. The fact that he saw as much as he did is a testament to his skill and patience as an observer. He spent night after night, sometimes in freezing cold, squinting through that imperfect tube, sketching what he saw, checking and rechecking his observations. Science has always been as much about persistence as about genius. The news spread through Europe slowly at first, then with gathering speed as other astronomers obtained telescopes and confirmed what Galileo had reported. The Milky Way was composed of stars. This fact filtered into the intellectual discourse of the era, challenging philosophers and theologians who had built elaborate systems around the idea of a perfect, unchanging heavens. If the Milky Way was just stars, if that divine, mystical band was made of ordinary matter, what else might the ancients have gotten wrong? You shift again on the grass and a shooting star streaks across your peripheral vision. You almost miss it, lost as you are in the past, but some part of your brain registers the flash and feels a small thrill of recognition. That was a meteor, a grain of space dust burning up in the atmosphere. Another thing Galileo's generation was only beginning to understand. The sky was becoming demystified, piece by piece, revelation by revelation. But knowing the Milky Way was made of stars still left the biggest question unanswered. What was its shape? What was its size? Where did it end, if it ended at all? Galileo couldn't answer these questions. His telescope could resolve nearby regions of the band into individual stars, but it couldn't tell him how far away those stars were, or how they were arranged in three-dimensional space. For that, astronomers would need better instruments, better mathematics, and a lot more patience. The historical debate about Galileo's legacy is more nuanced than popular accounts suggest. Historians still argue whether he genuinely believed in the Copernican system from the beginning, or came to it gradually through observation, whether his conflicts with the Church were primarily scientific or political, whether he was a martyr for truth or a difficult personality who made enemies unnecessarily. What's not in dispute is the impact of his telescopic observations. After 1610, the sky was no longer a painted dome. It was a space, a vast, perhaps infinite space, filled with objects that could be studied, measured, and eventually understood. And that understanding was about to take its next great leap forward, thanks to a man who would stand outside on cold English nights, counting stars one by one until his eyes ached and his fingers went numb, all in pursuit of a question that had never been answerable before. What is the shape of the universe itself? The cold is starting to seep through your clothing now, but you don't mind. There's something pleasant about it, a reminder that you have a body, that you exist in a specific place and time, even as your mind wanders through centuries. The stars above you seem to pulse gently, though that's just atmospheric distortion, the same phenomenon that makes them twinkle. Somewhere in the distance an owl calls, low and questioning, and you find yourself smiling at the sound. We're in England now, more than a century and a half after Galileo's revelations, and a German-born musician named William Herschel is about to become one of the most important astronomers in history. Herschel was a fascinating character. He emigrated to England in his 20s, made his living as an organist and composer, and only turned to astronomy as a hobby in his mid-30s. But what a hobby it became, working with his sister Caroline, who deserves far more recognition than history has given her. Herschel built telescopes of unprecedented size and quality. His largest, with a mirror 40 feet in focal length, was the biggest in the world for 50 years. And with these telescopes, Herschel set himself a task that bordered on madness. He would map the entire visible sky by counting stars. Think about that for a moment. No photography existed yet. No automated recording equipment. Just a man and his sister beside him, writing down everything he dictated, spending night after night, year after year, looking through a telescope and counting points of light. In specific regions, he would systematically record how many stars appeared within the field of view, then move the telescope slightly and count again. By comparing the density of stars in different directions, he hoped to determine the shape of the stellar system to which the Sun belonged. The method was brilliant in its simplicity and exhausting in its execution. Herschel eventually catalogued hundreds of thousands of observations, identifying new nebulae, double stars, and other phenomena along the way. Caroline herself discovered 8 comets, becoming one of the first professional female astronomers in history, though her contributions were often attributed to her brother or overlooked entirely. Historians still argue about the degree to which Herschel's fame obscured Caroline's achievements, a debate that has gained new urgency in an era more attentive to the erasure of women from scientific history. Based on his star counts, Herschel proposed that the Milky Way was shaped like a grindstone, a flattened disk thicker in the middle, with the Sun located somewhere near the centre. This was remarkably close to the truth in some respects and wildly wrong in others. He got the disk shape right. He got the central position of the Sun completely wrong. Our star is actually located about 2/3 of the way out from the galactic centre, but he had no way of knowing this. His method assumed that space was transparent, that he could see equally far in all directions, and that all stars were roughly the same intrinsic brightness. None of these assumptions were accurate. The problem was dust, interstellar dust, tiny particles of carbon, silicon, ice, and other materials floating in the void between stars absorbs and scatters light, making distant objects appear dimmer or hiding them entirely. Herschel couldn't see through the thick clouds of dust that lie between us and the galactic centre, so he thought he was observing the edge of the stellar system when he was actually just observing the limits of his visibility. It's a bit like standing in fog and concluding that the world ends where your vision fails. A reasonable inference, but fundamentally mistaken. Still, Herschel's work represented an enormous leap forward. For the first time, someone had attempted to determine the structure of the stellar universe through systematic observation rather than philosophical speculation. He demonstrated that the question was answerable in principle, even if his specific answer was flawed, and he established a methodology, careful counting, systematic coverage, mathematical analysis that would guide astronomy for generations to come. There's a lovely quirky fact about Herschel that doesn't make it into most history books. He was a devoted believer in extraterrestrial life, convinced that every celestial body, including the Sun, was inhabited by intelligent beings. He thought sunspots were openings in a luminous outer atmosphere, revealing a cool, habitable surface beneath. This seems laughable now, but it made a certain kind of sense given the knowledge of his time. If stars were suns and our sun supported life, why shouldn't other suns do the same? The logic was impeccable, only the premises were wrong. You feel your eyelids growing heavier, and you let them droop for a moment, not closing entirely but just resting, filtering the starlight through your lashes into soft blurs. The Milky Way stretches above you still, patient, waiting, containing all those stars that Herschel spent his life trying to count. He didn't finish the task. Nobody could finish it, not with eyes and patience alone. But he took the first steps on a journey that would eventually reveal our galaxy's true enormity, a journey that required not just bigger telescopes, but entirely new ways of thinking about distance, about light, and about the nature of the universe itself. The next major leap would come in the early 20th century, in a debate that would shake astronomy to its foundations and answer a question that had haunted scientists for decades. Were those mysterious spiral nebulae part of our stellar system, or were they something else entirely? The answer would make Herschel's grindstone look like a grain of sand on an infinite beach. The owl has gone quiet now, perhaps found its prey, perhaps simply decided that the night was too peaceful to interrupt. The grass beneath you has warmed slightly from your body heat, creating a small pocket of comfort in the cool darkness. Above, the Milky Way continues its slow arc across the sky, though you'd have to watch for hours to notice the movement. Everything in space seems so still when you're inside the system, looking out. It's only when you step back, conceptually, mathematically, that the motion becomes apparent. We're in Washington, D.C. now, in the year 1920, and two astronomers are about to have an argument that will change everything. The Great Debate, as it came to be known, took place on April 26th in the auditorium of the Smithsonian Museum of Natural History. On one side stood Harlow Shapley, a young and confident astronomer from the Mount Wilson Observatory in California. On the other stood Heber Curtis, an older and more cautious researcher from the Lick Observatory. The question they were there to debate sounds almost quaint now. How big is the universe? But understand the context. By 1920, astronomers had discovered thousands of fuzzy objects in the sky that they called nebulae, from the Latin word for cloud. Some of these nebulae were clearly clouds of gas, the kind of stellar nurseries we now know produce new stars, but others had a distinctive spiral structure, pinwheel shapes that seemed to suggest rotation, organization, something more than random gas. Were these spiral nebulae located within our own stellar system, making the Milky Way essentially the entire universe? Or were they separate systems, island universes, as the philosopher Immanuel Kant had speculated more than a century earlier, each one comparable in size to our own galaxy? Shapley argued forcefully for the first position. He had done groundbreaking work on globular clusters, those dense spherical collections of ancient stars that orbit the Milky Way, and had used them to estimate the galaxy's size at about 300,000 light-years across. This was much larger than previous estimates, and made the Milky Way seem vast enough to contain everything. The spiral nebulae, Shapley believed, were relatively small and nearby, perhaps objects in the process of forming into new solar systems. Curtis took the opposite view. He pointed out that the spiral nebulae seemed to avoid the plane of the Milky Way. There were far fewer of them visible near that band of light than in other parts of the sky. This suggested they were distant objects, obscured by the dust and gas of our own galaxy when we tried to look through it. He also noted that novae, sudden brightenings of stars, had been observed in spiral nebulae, and if these were similar to the novae seen in our own galaxy, then the distances involved would have to be immense. The debate itself was more complicated and less decisive than the dramatic retelling suggest. Neither astronomer delivered a knockout blow. Both made good points, and both made errors. Shapley overestimated the size of the Milky Way and underestimated the distances to the spiral nebulae. Curtis had better instincts about the nebulae but less impressive data to support his position. Historians still argue about who won the debate in any meaningful sense, and the truth is that the question wasn't settled that night in Washington. It would take another few years and another astronomer entirely to provide the definitive answer. But the debate crystallized something important. The question of scale had become central to astronomy. This wasn't just about cataloguing objects anymore. It was about understanding the fundamental architecture of reality. Was our galaxy everything, or was it just one island in an archipelago that might extend forever? The philosophical stakes were enormous. If the spiral nebulae were separate galaxies, then the universe was not merely large, but incomprehensibly, almost absurdly large. The word universe would have to be redefined to accommodate distances that made light itself seem slow. You feel a slight breeze stir the air around you, carrying the scent of grass and distant rain. The night seems to be holding its breath, waiting for something. In the story we're telling, that something is about to arrive, the evidence that would settle the debate once and for all and send human understanding of the cosmos expanding faster than anyone could have imagined. Here's a quirky historical footnote. Shapley and Curtis weren't actually debating each other in the traditional sense. The format was more like two consecutive lectures on the same topic, with each astronomer presenting his view separately. The dramatic confrontation that gets described in popular accounts is somewhat exaggerated. Real science rarely has the clear narrative structure we impose on it afterward. It's messier, more collaborative, more filled with dead ends and lucky accidents than the heroic stories suggest. But some stories deserve their drama, and the next chapter of this one involves a man named Edwin Hubble, a telescope on a California mountain, and a discovery that would reveal the Milky Way to be just one galaxy among billions, a cosmic citizen rather than a cosmic emperor. The evening air carries that particular quality of deep night now, when even the insects have settled into silence and the world seems suspended between one day and the next. You're still lying there on the grass, but your sense of scale has been shifting, stretching, as the history unfolds above and around you. What seemed like a comforting band of light has begun to feel more mysterious, more vast, more populated than you ever quite realized before. Mount Wilson rises above Los Angeles like a sentinel, its peak often clear while the city below drowns in smog and light pollution. In the 1920s, it was home to the most powerful telescope in the world, the Hooker telescope with a mirror 100 inches across. And in the autumn of 1923, a man named Edwin Hubble pointed that magnificent instrument at the Andromeda Nebula and found something that would reshape humanity's understanding of the cosmos. Hubble was looking for novae, those sudden stellar brightenings that Curtis had mentioned in the Great Debate. If he could find enough of them in Andromeda, he might be able to estimate its distance. What he found instead was something far more valuable, a Cepheid variable star. Cepheid variables are cosmic lighthouses. They're stars that pulse in brightness over regular periods, swelling and contracting like slow heartbeats. And here's the crucial discovery that made them so useful. A woman named Henrietta Swan Leavitt, working at Harvard College Observatory, had discovered in 1912 that the period of a Cepheid's pulsation was directly related to its intrinsic brightness. A Cepheid that pulsed slowly was genuinely brighter than one that pulsed quickly. This meant that if you could measure how long a Cepheid took to complete its cycle, you could calculate how bright it actually was. And if you knew how bright it actually was, you could compare that to how bright it appeared and calculate how far away it must be. This was revolutionary. For the first time, astronomers had a reliable standard candle, a type of object whose true brightness was known, allowing distance to be measured directly. Leavitt never received the recognition she deserved in her lifetime. She died of cancer in 1921, just 2 years before Hubble used her discovery to transform cosmology. Historians still argue about whether she would have received a Nobel Prize had she lived longer — the prize cannot be awarded posthumously — and about whether her contributions were adequately acknowledged by her male colleagues. The evidence suggests they were not. Hubble found his Cepheid in Andromeda, measured its period, calculated its intrinsic brightness, and then compared that to its apparent brightness. The math was unambiguous. The star was far too faint to be located within our own galaxy, even using Shapley's inflated estimates. It had to be at least 900,000 light-years away, well beyond the boundaries of the Milky Way by any reasonable measure. Andromeda was not a nebula within our galaxy. It was a galaxy in its own right, a vast collection of stars comparable to our own, separated from us by a gulf of space that made all previous astronomical distances seem trivial. The universe had just become incomprehensibly larger. Hubble announced his findings in early 1925, and the astronomical community took notice. Some resisted at first. Shapley, whose career had been built partly on the idea of a large but solitary Milky Way, was initially sceptical, but the evidence was overwhelming. Over the following years, Hubble and others identified Cepheus in more and more spiral nebulae, and every measurement pointed to the same conclusion. These were independent galaxies, scattered through space at distances measured in millions of light years. The island universe hypothesis had been confirmed. The Milky Way was not the universe entire, but merely one island in an ocean that stretched beyond imagination. You feel something loosen in your chest as you contemplate this, some tension you didn't know you were holding. There's something both terrifying and liberating about smallness on this scale. Your problems, your worries, your daily anxieties, they exist on a mote of dust circling an unremarkable star in one galaxy among billions. This could be depressing, but lying here in the quiet darkness, feeling the planet turn beneath you, it feels more like freedom. You matter exactly as much as you ever did, which is to say, enormously, to the people who love you, and not at all to the cold equations of space and time. Both things are true. Both things can coexist. Hubble went on to make even more astonishing discoveries, including the observation that distant galaxies were receding from us at speeds proportional to their distance. The first evidence for the expanding universe that would eventually lead to the Big Bang theory. But that's a story for another night. For now, what matters is this. By 1925, humanity knew that the Milky Way was just one galaxy among many. The question was no longer whether other galaxies existed, but how many there were and how far they extended. The answer, as we now know, is far more than Hubble ever imagined, extending far beyond anything visible even to the most powerful telescopes of his era. The observable universe contains an estimated 2 trillion galaxies. 2 trillion, each one containing billions of stars. The numbers become meaningless at a certain point, too large for human intuition to grasp. But we'll keep trying anyway, you and I, because that's what humans do. We reach for understanding even when understanding seems impossible. The breeze has died down again, and the night has settled into that profound stillness that only exists in the hours when most of the world is sleeping. Your body has relaxed further into the grass, and the stars above seem closer somehow, as if they've descended just a little to keep you company. The Milky Way stretches from horizon to horizon. That ancient band of light you now know is home to hundreds of billions of suns. But just how wide is home? Let's talk about the Milky Way's diameter, and let's try to make numbers that should be meaningless actually mean something. The current scientific consensus places our galaxy's diameter somewhere between 100,000 and 200,000 light years. That's a surprisingly large range for something so fundamental, and the uncertainty tells you something about how difficult these measurements actually are. We can't step outside the galaxy to measure it with a cosmic ruler. We're stuck inside, like ants trying to determine the size of their anthill without ever leaving it, inferring the whole from the parts we can observe. Let's start with the smaller estimate, 100,000 light-years across. A light year, you probably remember, is the distance light travels in 1 year, about 5.88 trillion miles. So 100,000 light-years is roughly 588 quadrillion miles. Written out, that's 588 trillion miles. The number is so large that it conveys nothing. It's just zeros. Try this instead. Imagine you could drive across the galaxy in a car travelling at highway speed, say 60 miles per hour, without stopping for gas or sleep, or the basic human need to not be in a car for eternity. At that speed, crossing the Milky Way would take about 1.1 trillion years. That's 1,100 billion years. The universe itself is only about 13.8 billion years old. you'd run out of universe before you finished your road trip by a factor of about 80. Or try light itself, the fastest thing that exists, the cosmic speed limit. A photon leaving from one edge of the galaxy, travelling at 186,000 miles per second, would take at minimum 100,000 years to reach the other side. Every time you look at a star in the night sky, you're seeing ancient light, photons that left their source years or decades or centuries ago, and only now are arriving at your eyes. The light from some of the stars visible in the Milky Way tonight began its journey before humans invented writing, before the pyramids were built, before the last ice age ended. But recent research has pushed the diameter estimate significantly higher. Studies of the galaxy's outer reaches, particularly the faint halo of old stars and dark matter that surrounds the visible disk, suggest the Milky Way might extend to 200,000 light-years or more. The disk itself, the thin, bright region where most of the stars and gas reside, is only part of the story. There's a spherical halo surrounding it, populated by ancient globular clusters and individual old stars, and this halo extends far beyond the disk's edge. There's also that invisible dark matter halo, which we'll discuss soon, and that extends further still. Historians of astronomy sometimes note that every estimate of the galaxy's size in history has turned out to be too small. Herschel thought it was a few thousand light-years across. Kapteyn, in the early 20th century, thought 30,000. Shapley pushed it to 300,000, which turned out to be an overestimate in some respects but an underestimate in others. The pattern suggests humility. Whatever number we've settled on now might itself be revised upward as our instruments improve. Here's a quirky fact that puts the scale in perspective. The Voyager 1 spacecraft, launched in 1977, is the most distant human-made object in existence. As of now, it's about 15 billion miles from Earth, travelling at roughly 38,000 miles per hour. At that speed, it would take Voyager about 1.7 billion years to cross the Milky Way. The spacecraft will likely cease functioning within the next decade as its plutonium power source decays, but its remains will continue drifting through interstellar space, a tiny metal emissary from a species that barely registers on the cosmic scale. Scientists still argue about the exact boundary of the Milky Way. Where does our galaxy end and intergalactic space begin? There's no sharp edge, no fence marking the property line. The density of stars simply decreases as you move outward, thinning and thinning until eventually you're in the void between galaxies, where the nearest star might be millions of light-years away. But even in that void, you'd still be within the gravitational influence of the Milky Way, still technically part of its extended family. You stare up at the band of light above you, trying to hold the number in your mind. 100,000 light-years, 200,000. It doesn't matter which estimate is correct. Either one exceeds comprehension by such a margin that the difference is academic. What matters is this: you are small beyond imagination, embedded in a structure so vast that your entire life, your entire civilization, your entire species represents less than a blink in its history. And yet here you are, thinking about it, understanding it, at least in some abstract mathematical way. That's remarkable. That's something worth celebrating, even as the scale makes celebration seem absurd. The stars seem to shift slightly above you, though that's probably just your eyes adjusting, finding new details in the darkness. Your breathing has slowed to match the rhythm of the night, deep and regular, as if your body has decided that the best response to cosmic immensity is to simply relax into it. The grass is cool beneath you, the earth solid and reassuring, and the Milky Way spreads overhead like a promise of infinite distance. But here's something that might surprise you. Most of what you're looking at isn't actually there. Or rather, what you're looking at, the stars, the gas, the dust, is only a small fraction of what the galaxy actually contains. The rest is invisible. We call it dark matter, and it might be the strangest discovery in the history of astronomy. The story begins in the 1930s with a Swiss astronomer named Fritz Zwicky, who had a talent for being right about things before anyone believed him. Zwicky was studying galaxy clusters, groups of galaxies bound together by gravity, and he noticed something peculiar. When he calculated the mass of the Coma cluster based on the brightness of its member galaxies, he got one number. But when he calculated the mass based on how fast those galaxies were moving, he got a much larger number. The galaxies were orbiting the cluster's centre too quickly, as if there was much more gravitational pull than the visible matter could account for. Zwicky called this missing mass Dunkelmaterie, dark matter, and proposed that the cluster contained a huge amount of invisible material. The astronomical community largely ignored him. Zwicky was a brilliant but difficult personality, prone to calling his colleagues spherical bastards. Bastards, he explained, no matter which way you looked at them. And his dark matter idea seemed too radical to take seriously. For decades it languished as a curiosity, a problem to be solved later, or perhaps explained away with better observations. Then, in the 1970s, an American astronomer named Vera Rubin turned her attention to spiral galaxies, including our own. She was measuring how far stars orbited the galactic centre at various distances. According to the laws of gravity, stars farther from the centre should orbit more slowly, just as planets farther from the Sun orbit more slowly than those nearby. But that's not what Rubin found. The rotation curves, the graphs showing orbital speed versus distance, were flat. Stars at the outer edges of galaxies were moving just as fast as stars close to the centre, as if the mass of the galaxy didn't drop off with distance but remained constant. The only explanation that made sense was that galaxies were embedded in vast halos of invisible matter, providing additional gravitational pull that kept those outer stars moving quickly. The dark matter wasn't scattered evenly throughout the galaxy, but formed a spherical cocoon around it, extending far beyond the visible disk. And there was a lot of it. By current estimates, dark matter makes up about 85% of the Milky Way's total mass. The stars and gas and planets you can see, including the Sun, including Earth, including you, represent just 15% of what our galaxy actually contains. What is dark matter? That's one of the great unsolved questions in physics, and scientists still argue fiercely about it. We know what it isn't. It's not ordinary matter that happens to be dark, like burned out stars or clouds of cold gas. Those possibilities have been ruled out by various observations. It's also not antimatter or black holes in sufficient quantities to explain the missing mass. The leading hypothesis is that dark matter consists of some new type of subatomic particle that interacts with gravity but not with light or ordinary matter. These hypothetical particles, sometimes called WIMPs, weakly interacting massive particles, would pass through normal matter like ghosts, billions of them flowing through your body every second without leaving a trace. You shiver slightly, though whether from cold or from the thought of invisible particles passing through you, you're not sure. It's an eerie idea. The galaxy you live in, the structure you can see spread across the sky above you, is mostly composed of something you can never see, touch, or detect directly. We know it's there because of its gravitational effects, the way we might know an invisible person is in a room because we see the chair cushion compress when they sit down. But we've never captured a dark matter particle, never detected one in a laboratory, never found a way to prove definitively what it is. Some researchers have proposed alternative theories that modify the laws of gravity rather than positing invisible matter. These modified Newtonian dynamics, or MOND theories, have their adherents, but they struggle to explain all the observations as elegantly as dark matter does. The debate continues in physics departments and at conferences around the world, one of those arguments that might be settled in the next decade or might take another century. Here's a quirky thought experiment. If you could remove all the dark matter from the Milky Way instantly, the galaxy would fly apart. The visible matter doesn't have enough gravitational pull to hold everything together. Stars would scatter into intergalactic space, the beautiful spiral structure would dissolve, and the Sun, with Earth in tow, would drift off on a lonely journey through the void. Dark matter isn't just present in our galaxy, it's essential. Without it, there would be no galaxy at all. The thought of 400 billion suns floats through your mind like a dandelion seed, light and untethered, impossible to grasp firmly. The number is too large. Your brain, evolved to track perhaps 100 social relationships and count perhaps a few thousand objects, has no category for 400 billion. It's just noise, a string of syllables that conveys scale without actually meaning anything. Let's try to make it mean something. 400 billion is the current estimate for the number of stars in the Milky Way galaxy. It's not a precise count. How could it be when we can't see most of the galaxy directly, but rather an inference based on the galaxy's total mass, brightness, and structure? Some estimates range as low as 100 billion, others as high as 400 billion or more. The uncertainty is enormous, but even the lowest estimate is so far beyond everyday experience that the difference hardly matters. Imagine you wanted to count all the stars in the galaxy, one by one. You're a dedicated counter, willing to work 8 hours a day, every day without breaks. You can count quickly, 1 star per second, which is optimistic given that you'd need to somehow identify and track each one. At that pace, 1 star per second, 8 hours a day, it would take you about 34,000 years to count to 1 billion. To count to 400 billion would take approximately 13.7 million years. The entire history of modern humans, every civilization, every invention, every war, every love story, fits within about 300,000 years. You'd need to repeat human history more than 45 times over to finish counting. Or try this. There are roughly 7.9 billion people on Earth. If every single person alive today counted 1 star, you'd only get through about 2% of the galaxy's total. You'd need the combined population of about 50 Earths to have enough counters for 1 star each. The numbers resist comprehension. They're too big, too far outside the scale at which human intuition operates. Psychologists call this scope insensitivity, our inability to emotionally process large numbers as different from each other. A million feels about the same as a billion feels about the same as a trillion. They're all just a lot. But each of those 400 billion stars is a sun. Many of them are larger than our own sun. Many are smaller. Some are ancient, red and cool, burning through the last dregs of their hydrogen fuel. Others are young and blue, so massive they'll exhaust themselves and explode within a few million years. Some have planets, potentially billions of planets, and some of those planets might harbour life. The Milky Way is not just a collection of lights. It's a collection of furnaces, forges, nurseries and graveyards, a dynamic ecosystem of birth and death and change playing out across distances that mock human timescales. Historians of astronomy note that star counts have increased dramatically with each improvement in technology. Early estimates in the pre-telescopic era numbered the visible stars at about 6,000, roughly correct for what the naked eye can see from a dark location. Telescopes pushed the count into the millions, then the hundreds of millions. Spectroscopy and photography pushed it higher still. Modern surveys using infrared light, which can penetrate the dust that obscures much of the galaxy, have pushed estimates toward that 400 billion figure. And even now, scientists still argue about the true number, with some suggesting the Milky Way might contain as many as 1 trillion stars if you include all the faint red dwarfs that our surveys might miss. Here's a quirky fact that puts things in perspective. There are more stars in the Milky Way than there are grains of sand on all the beaches of Earth. This sounds like it must be an exaggeration, but mathematicians have done the calculations. The number of sand grains on Earth's beaches is estimated at roughly 7.5 quintillion. A big number to be sure, but the universe is bigger, and the Milky Way is just one galaxy among perhaps 2 trillion in the observable universe. The total number of stars out there approaches something like 1 septillion, a 1 followed by 24 zeros. That's more stars than there are grains of sand on every beach of 10,000 Earths. You let out a long, slow breath, feeling your chest rise and fall, grounding yourself in the simple reality of your own body. Somewhere out there, in that band of a light above you, nuclear fusion is happening on a scale that defies imagination. Hydrogen atoms are being crushed together into helium, releasing energy that eventually becomes the starlight reaching your eyes. It happened 8 minutes ago in the case of our own sun. It happened thousands of years ago in the case of stars on the far side of the galaxy. Time and space blend together at these scales, past and present becoming meaningless distinctions when the distances involved are measured in light years. And you're seeing all of it, or at least the fraction that your eyes can detect, lying on cool grass on a small planet, with crickets maybe starting to chirp again in the distance. The contrast is absurd. The universe doesn't care about that absurdity. It simply is. The night has deepened, if such a thing is possible, settling around you like a familiar blanket. You've been lying here long enough that your eyes have fully adapted to the darkness, picking out details in the Milky Way that you couldn't see when you first stepped outside. The band of light is no longer uniform. You can see variations in brightness, dark patches where something blocks the stars behind, richer and paler regions like cream swirled incompletely into coffee. And somewhere in all that light, there's a very ordinary yellow star called the Sun, and around it, a small blue planet called home. Where exactly are you in this vast spiral city of stars? Our solar system is located in what astronomers call the Orion Spur, sometimes the Orion Arm, a minor spiral feature between two of the Milky Way's larger arms, the Sagittarius Arm and the Perseus Arm. Think of it as a suburb, a side street off the main galactic highway. We're not in a prestigious central location, not close to the bustling downtown of the galactic core. We're in the outskirts, the quiet neighbourhoods, where nothing much happens and the real estate is relatively cheap, cosmically speaking. This might sound disappointing, like learning your house is in an unfashionable part of town, but for life, it's actually ideal. The galactic centre is a dangerous place crowded with stars bathed in radiation, disturbed by the gravitational influence of the supermassive black hole lurking there. Supernovae, the explosive deaths of massive stars, happen more frequently near the centre, sterilising any planets unlucky enough to be caught in the blast. The outer regions, by contrast, tend to lack the heavy elements necessary for rocky planets and complex chemistry. Our location in the middle ground, in a quiet arm about 26,000 light-years from the galactic centre, provides a stable, relatively safe environment with enough heavy elements to build planets like Earth. This is sometimes called the galactic habitable zone, and scientists still argue about its exact boundaries and whether it's a meaningful concept at all. The idea is that life, or at least complex life, might only be possible in certain regions of a galaxy. Not too close to the centre, not too far out, not too near recent supernova or other catastrophic events. Our solar system has occupied this zone for billions of years, stable and undisturbed, giving life time to emerge and evolve. Whether this is coincidence or cosmic inevitability is one of those questions we can't yet answer. The Sun, along with its planets, orbits the galactic centre at a speed of about 500,000 miles per hour. That sounds fast, and it is, compared to the terrestrial speeds. But the galaxy is so large that even at this velocity, it takes about 230 million years to complete one orbit. This period is sometimes called a galactic year, and the Sun has completed only about 20 galactic years since it formed 4.6 billion years ago. Dinosaurs roamed the Earth less than 1 galactic year ago. The earliest single-celled life appeared roughly 17 galactic years ago. The entire history of complex multicellular life fits within a single circuit around the galaxy. You try to feel this motion, lying there on your patch of grass. You can't, of course. The Earth's rotation on its axis is imperceptible without instruments. The orbital motion around the Sun is even harder to sense, and the galactic orbit is completely invisible, a slow drift through the cosmos that affects nothing you can experience directly. But it's happening nonetheless. Right now, you're moving at 500,000 miles per hour relative to the galactic centre, following a path that has been traced by the Sun since before there was a Sun, since the cloud of gas and dust that would become our solar system first coalesced in this suburban arm of the Milky Way. Here's a quirky fact about our galactic address. The Orion Spur, though considered a minor feature, is actually enormous by human standards. It stretches about 3,500 light-years in length and 10,000 light-years across. The constellation Orion, visible in the night sky, contains several stars that are our neighbours within this spur: Betelgeuse, Rigel, the stars of Orion's belt. When you look at Orion, you're looking at your own cosmic neighbourhood, the local region of the arm where your star was born. The historical debate about the sun's position in the galaxy took decades to resolve. Remember Herschel counting stars by hand, placing the sun near the galaxy's centre? That mistake persisted in various forms into the 20th century. It was Harlow Shapley, using globular clusters as markers, who first correctly deduced that we were far from the centre. His estimate of our distance was somewhat off. He thought we were about 50,000 light-years out compared to the modern value of 26,000. But he got the basic picture right. We are not central. We are peripheral. The universe does not revolve around us. The Milky Way spreads above you, indifferent to your position within it, containing your entire world in its vast spiral architecture. Somewhere in that glow, the sun is moving, and with it, the 8 planets and countless smaller objects that make up our solar system. You're on the ride whether you chose to be or not. The galactic centre calls to you now, pulling your attention inward along that band of light toward the densest, brightest region, hidden behind veils of dust but blazing with invisible power. If the Milky Way were a city, this would be Times Square at midnight. Crowded, chaotic, brilliant, dangerous. And at its heart, something extraordinary waits. Sagittarius A star, pronounced A star, is the supermassive black hole at the centre of our galaxy. It contains the mass of about 4 million suns compressed into a region smaller than the orbit of Mercury. And for most of human history, we had no idea it was there. The concept of black holes emerged from Einstein's theory of general relativity in 1915, but for decades they remained theoretical curiosities, mathematical possibilities that might not exist in nature. It wasn't until the 1970s that astronomers began to suspect something unusual lurked at the Milky Way's core. Radio observations revealed a compact, powerful source of radiation there, too energetic to be an ordinary star cluster, too small to be a cloud of gas. Theories multiplied. Some proposed a dense concentration of stellar remnants. Others suggested something more exotic. The breakthrough came through patience and precision. Over several decades, astronomers tracked the orbits of stars near the galactic centre, using infrared telescopes that could peer through the intervening dust. One star in particular, designated S2, proved crucial. S2 orbits Sagittarius A star with a period of about 16 years, approaching within about 17 light-hours of the central object, closer than Pluto is to the Sun. By mapping S2's orbit precisely, astronomers could calculate the mass of whatever it was orbiting. The answer was unambiguous: about 4 million solar masses, compressed into a volume that ruled out everything except a black hole. In 2022, the Event Horizon Telescope collaboration released an image of Sagittarius A star itself, or rather, of the glowing gas swirling around it, illuminating its shadow. The image shows a blurry orange ring, not because the telescope was poor, but because the black hole's gravity bends light in complex ways, warping space itself around the event horizon. It was the first direct visual evidence of our galaxy's central engine, confirmation that the thing theoretical physics had predicted actually existed. What would it be like to visit Sagittarius, a star? You wouldn't want to, honestly. As you approached, the gravitational gradient, the difference in pull between your head and your feet, would stretch you like taffy in a process colourfully called spaghettification. Before that happened, radiation from the superheated gas spiralling into the black hole would cook you, and even if you survived both, crossing the event horizon would mean the end of any possible return. Not even light can escape from within that boundary. But the black hole isn't actively feeding right now, not much anyway. Compared to the supermassive black holes at the centres of some galaxies, the ones that power quasars and active galactic nuclei, blazing with the light of entire galaxies concentrated into a single point, Sagittarius A star is relatively quiet. It's snacking, not feasting, consuming only modest amounts of gas and dust. This might not always have been the case. Evidence suggests that in the past the Milky Way's central black hole was more active, producing jets of material and bursts of radiation that would have lit up the night sky for observers on distant planets. Historians of astronomy find it remarkable how quickly black holes went from theoretical speculation to established fact. Einstein himself doubted they could actually form. He published a paper in 1939 arguing that matter couldn't collapse into such a configuration. He was wrong, but forgivably so. The physics involved was new and counterintuitive. Scientists still argue about the internal structure of black holes, about what happens to information that falls in, about whether singularities actually exist or are just mathematical artifacts of incomplete theories. Here's a quirky fact about Sagittarius A. Despite its enormous mass, it's invisible to the naked eye. The dust between us and the galactic centre is so thick that visible light cannot penetrate it. If you could magically remove all that dust, the central region of the Milky Way would blaze like a searchlight, thousands of times brighter than it appears now. The view would be spectacular, and the radiation would probably be harmful. Perhaps it's best that we can't see. You feel the weight of the black hole in your imagination, a presence lurking in the heart of the galaxy, shaping orbits, influencing structure, ancient and patient. 4 million suns worth of matter collapsed into a point, waiting at the centre of the spiral. The Milky Way spins around it like water around a drain, though on timescales so long that the metaphor breaks down. Nothing is rushing. Everything is slow, patient, cosmic. You let your eyes trace the spiral arms of the Milky Way, or at least the parts you can see from inside, which is mostly just a band of light with brighter and dimmer regions. But from outside, from a perspective we can only imagine, our galaxy would be beautiful. A vast pinwheel of light, arms sweeping out in graceful curves, studded with young blue stars and glowing nebulae. It would look solid, structured, like a sculpture frozen in space. But here's the strange truth. The spiral arms aren't really there, not in the way you might think. When you look at a spiral galaxy in a photograph, it's easy to imagine the arms as permanent features, like the spokes of a wheel. You might picture stars locked into their arms, travelling along those curved paths forever, maintaining the spiral pattern like cars on a highway. But that's not what's happening. The spiral arms are density waves, patterns of compression moving through the galactic disk, and stars pass through them rather than travelling with them. Think of it like a traffic jam on a highway. Cars bunch up at a certain location. Maybe there's a merge or an accident or just too many vehicles, and the jam persists even though individual cars are constantly entering and leaving it. The cars that were in the jam an hour ago have long since driven away. The cars in the jam now will be gone in another hour. The jam itself is a pattern, not a collection of specific vehicles. Galactic spiral arms work similarly. They're regions where gravity creates higher than average density, pulling stars, gas and dust closer together. As material orbits the galactic centre, it passes through these density waves, slowing down slightly in the compressed regions before speeding up again on the other side. The arms persist even though no individual star remains in the same arm forever. Our own Sun has probably passed through several spiral arms over its 4.6 billion year lifetime, spending some periods in denser regions and others in the gaps between. This density wave theory was developed in the 1960s by astronomers C.C. Lin and Frank Hsu, and it elegantly explained why spiral patterns persist over billions of years, when simpler models suggested they should wind up and disappear. If the arms were material structures, they would indeed wind tighter and tighter with each galactic rotation, until they dissolved into a featureless disk. But as density waves, they maintain their shape, propagating through the galaxy like ripples in a pond. The compressed gas in spiral arms is where new stars form. When a cloud of hydrogen enters a density wave, the increased pressure can trigger gravitational collapse, igniting nuclear fusion in new stellar nurseries. This is why spiral arms appear so bright. They're populated by young, hot blue stars that formed recently from compressed gas. These massive stars burn out quickly, exploding as supernovae within a few million years, so they don't have time to drift far from the arms where they were born. Meanwhile, older, redder stars are distributed more evenly throughout the disk, having had billions of years to wander away from their birthplaces. Scientists still argue about some aspects of spiral structure. Not all spiral galaxies fit the density wave model neatly. Some seem to have tidally induced arms from gravitational interactions with neighbours, while others might develop transient spiral patterns that form and dissolve over time. The Milky Way's own spiral structure has been particularly difficult to map because we're inside it, unable to step back and see the full picture. Estimates of how many spiral arms we have ranged from 2 to 4, and the exact shape and position of these features remain subjects of ongoing research. Here's a quirky visualization that might help. Imagine you're a mote of dust riding on a vinyl record as it spins. From your perspective, the grooves seem fixed and permanent, features of your environment. But the grooves aren't moving with the record, they're patterns impressed into it, and as the record spins, you pass through groove after groove without any groove moving along with you. Galactic spiral arms are like those grooves, structures in space that stars and gas move through rather than structures made of specific stars and gas. You watch the Milky Way above you with new eyes now, knowing that the apparent stability of that band of light conceals constant motion. Stars are streaming through density waves, clouds of gas are collapsing into new suns, ancient stars are drifting slowly outward over billions of years. Nothing is fixed, nothing is permanent. The galaxy is a dynamic system, churning and changing on timescales that make human history look like a freeze frame. The spiral arms will still be there when you wake tomorrow, and when your grandchildren look up, and when species that haven't evolved yet wonder at the night sky millions of years from now. But they won't be the same arms, not exactly. The pattern persists while everything within it flows. The Milky Way doesn't exist in isolation. Nothing does, really. The universe is a web of connections, gravitational threads linking every massive object to every other. But the Milky Way has a particular neighbourhood, a group of cosmic companions bound together in a structure called the local group. The local group is our galactic suburb, a collection of about 80 galaxies spread across roughly 10 million light-years of space. That sounds like a lot, but by galactic standards it's a cosy cluster. Many of these 80 galaxies are small, dwarf galaxies they're called, containing only millions or billions of stars compared to the Milky Way's hundreds of billions. But a few are substantial, and 2 of them rival or exceed our own galaxy in size. The largest member of the local group is the Andromeda galaxy, also known as M31. You can see it with the naked eye on a clear night, a faint smudge of light in the constellation Andromeda, the most distant object visible without a telescope. What you're seeing when you spot that smudge is light from 1 trillion stars, photons that began their journey 2.5 million years ago, when our ancestors were just starting to figure out stone tools on the African savanna. Andromeda is bigger than the Milky Way, more massive, containing more stars. It's the giant of our local neighbourhood, and we're its largest neighbour. The third major galaxy in the local group is the Triangulum galaxy, M33, smaller than both Andromeda and the Milky Way, but still containing about 40 billion stars. Beyond these 3, the group consists mainly of dwarf galaxies, many of them satellites orbiting the larger members. The Milky Way alone has at least 50 known satellite galaxies, including the large and small Magellanic Clouds, visible from the southern hemisphere as detached patches of the Milky Way. The Magellanic Clouds deserve special mention. The Large Magellanic Cloud is about 160,000 light-years from Earth close enough that individual stars can be resolved and studied. It was in the Large Magellanic Cloud that the most recent naked-eye supernova occurred in 1987, SN 1987A, a stellar explosion bright enough to see without any instruments, the first such event since Kepler's supernova in 1604. That explosion gave astronomers an unprecedented opportunity to study stellar death up close, and its remnants are still being observed today. The local group is held together by gravity, all 80-odd galaxies bound in a gravitational dance that will continue for billions of years. This might seem like a peaceful arrangement, but it's not stable forever. Gravity doesn't just hold things in orbit, it also pulls things together, and the two largest members of the local group, the Milky Way and Andromeda, are approaching each other at about 250,000 miles per hour. We'll talk more about that collision in the next section, but for now consider the intimacy of our galactic neighbourhood. These are our nearest cosmic neighbours, the galaxies we've had the longest to study, the structures we understand best. When astronomers first began mapping the universe beyond the Milky Way, the local group was their starting point, the calibration reference against which larger distances were measured. Errors in understanding the local group propagated outward, affecting estimates of the size and age of the universe itself. Scientists still argue about the exact membership of the local group and its boundaries. New dwarf galaxies continue to be discovered, hiding in the glare of the Milky Way, or lurking in regions that surveys hadn't covered. The line between member of the local group and nearby galaxy not bound to the group is somewhat arbitrary, defined by gravitational influence rather than any sharp physical boundary. Here's a quirky fact. The local group has no single centre. Unlike a solar system, where everything orbits a dominant central mass, or a galaxy, where everything orbits a common centre of gravity, the local group is an anarchic collection. The Milky Way and Andromeda are both gravitationally dominant, each with their own retinue of satellites, and the group's overall motion reflects this shared governance. We're not orbiting anything. We're falling toward each other, slowly but inevitably. You think about neighbours, about the strange mixture of closeness and distance that neighbourly relationships entail. Your actual neighbours on Earth are a few dozen feet away, close enough to hear through walls, close enough to borrow sugar from. The Milky Way's nearest large neighbour is 2.5 million light-years away, and light itself is the only thing that can make that journey in any reasonable time. Yet these are our companions in the cosmos, the galaxies whose fates are linked to ours by invisible threads of gravity, the only other island universes that exist within our gravitational sphere of influence. The local group floats in the void, a small pocket of light in an ocean of darkness, waiting for whatever comes next. You drift back toward wakefulness slowly, not quite surfacing, held in that liminal space where sleep and consciousness mingle. The Milky Way is still above you. Of course it is. It hasn't gone anywhere in the few peaceful minutes since we paused, and the story continues as gently as before. We were speaking of neighbours, of the local group, of the strange gravitational bonds that link galaxies across millions of light-years of space. And we mentioned, perhaps ominously, that the Milky Way and Andromeda are approaching each other. Let's talk about that collision. Right now, at this moment, Andromeda is hurtling toward us at approximately 250,000 miles per hour. That sounds terrifying, and it is, if you imagine such a speed in human terms, but space is so vast that even at this velocity, the collision won't happen for about 4.5 billion years. That's roughly the same amount of time as the Sun has already existed. That's longer than complex life has been on Earth. That's a span of time so long that your imagination can't really grasp it, only approximate it with metaphors and comparisons that themselves fall short. So you have time. Humanity, if it still exists then in some form, will have time, but the collision will happen, gravity doesn't forget. What will it look like? This is where the surprising answer comes in. It will probably be spectacular, but it almost certainly won't be catastrophic. Despite containing hundreds of billions of stars, both galaxies are mostly empty space. The average distance between stars is so enormous, several light years typically, that when two galaxies merge, their stars pass through each other like two swarms of gnats, barely interacting at all. Computer simulations of galaxy mergers show this clearly. The stars glide past each other in complex gravitational dances, their paths bent by the combined mass but rarely colliding directly. The gas is another story. The diffuse clouds of hydrogen and helium that fill interstellar space will collide and compress, triggering massive bursts of star formation. The merged galaxy will probably blaze with young blue stars for millions of years as this compressed gas ignites. Eventually, after perhaps 1 billion years of gravitational chaos, the two spirals will settle into a single elliptical galaxy, a featureless blob of old stars with little of the elegant structure either parent once had. Astronomers have given this future galaxy a name, Milkomeda, or sometimes Milkdromeda. Neither name is official, and both are somewhat silly, but they capture the essential point. The Milky Way as we know it won't exist forever. Our galaxy is not a permanent structure but a temporary configuration, destined to transform through collision and merger into something unrecognizable. What about our solar system? Will Earth survive? The Sun won't, but that's unrelated to the galactic merger. By the time Andromeda arrives, the Sun will have already expanded into a red giant and likely swallowed Earth, or at least rendered it uninhabitable. But if we imagine a future humanity living somewhere else, orbiting a younger star, they could potentially watch the merger unfold over millions of years. The night sky would change gradually at first, Andromeda growing larger and brighter, then dramatically as the two galaxies passed through each other, splitting and reforming in tidal streams and gravitational whirls. Scientists still argue about the exact timeline and dynamics of the merger. Recent measurements using the Gaia satellite have refined our understanding of Andromeda's motion, suggesting the collision might be more of a glancing blow than a head-on impact. The Triangulum galaxy might be pulled into the chaos as well, contributing its mass to the final merged structure. Dark matter halos will interact in ways we can model, but not directly observe, influencing the merger's outcome through invisible gravitational forces. Here's a quirky fact. We can already see what this merger will look like by observing other galaxies in the process of colliding. The antennae galaxies, the mice galaxies, the tadpole galaxy, these are all systems caught in various stages of gravitational interaction, their shapes distorted into long tails and bridges of stars, their cores blazing with collision-triggered star formation. They're previews of our own galactic future, written in light that has travelled tens of millions of years to reach us. The collision feels distant, academic, a problem for being so far in the future they might not even be recognisable as our descendants. But there's something poignant about it nonetheless. The galaxy that gave birth to our solar system, the structure that has been humanity's cosmic home for as long as there have been humans to look up at it, will eventually cease to exist. Not destroyed, transformed, merged into something new. We need to zoom out further now, expanding our perspective from the intimate scale of the local group to structures so vast they make galaxies look like grains of sand. Hold on to something, conceptually at least, because the vertigo is about to intensify. The local group is part of a larger structure called the Virgo supercluster. This is a collection of about 100 galaxy groups and clusters, including the Virgo cluster itself, a massive gravitational concentration of over 1,300 galaxies located about 54 million light-years from Earth. The Virgo supercluster spans roughly 110 million light-years and contains thousands of galaxies, of which the Milky Way is just one tiny peripheral member. For a long time, the Virgo supercluster was thought to be our cosmic address at the larger scale, our galactic neighbourhood's neighbourhood, so to speak. But in 2014, astronomers published a paper that redrew the map entirely. Using careful measurements of how galaxies move through space, they discovered that the Virgo supercluster is itself just a small outlying component of a much larger structure, one they named Laniakea. Laniakea, the name comes from Hawaiian, meaning immeasurable heaven, is a supercluster of superclusters, a gravitational basin containing approximately 100,000 galaxies spread across 520 million light-years. That number is worth repeating, 520 million light-years. Light itself, travelling at the cosmic speed limit, would need 520 million years to cross from one end of Laniakea to the other. That's longer than complex life has existed on Earth. That's longer than the age of fish or amphibians or any creature that has ever walked or crawled or swum. The key to understanding Laniakea is gravity. All the galaxies within this structure are flowing toward a common gravitational centre, a region of space called the Great Attractor. The Great Attractor isn't a single object, but rather a region of unusual mass concentration, pulling everything nearby toward it at hundreds of kilometres per second. Our own local group is part of this cosmic flow, falling toward the Great Attractor along with thousands of other galaxies, all participating in a motion we can detect but couldn't directly see until recent advances in observational technique. The boundaries of Laniakea are defined not by physical barriers, but by watersheds in the cosmic flow. Imagine rain falling on a mountain range. Some drops flow east into one river basin, others flow west into another. The ridgeline defines the boundary between watersheds. Similarly, the boundaries of Laniakea are defined by the dividing lines between gravitational basins, regions where galaxies flow toward one attractor rather than another. Beyond Laniakea, other superclusters exist, each with their own internal flows and attractors. Scientists still argue about whether Laniakea is a stable, bound structure, or merely a transient pattern in the cosmic flow. The universe is expanding after all, and dark energy is accelerating that expansion. On large enough scales, this expansion might overwhelm gravitational attraction, preventing superclusters from ever collapsing into coherent structures. Laniakea might not be a place you could ever be from in any permanent sense, just a temporary neighbourhood defined by flows that will eventually be torn apart by the expanding universe. Here's a quirky fact about our cosmic address. If you wanted to mail a letter to Earth from outside the observable universe, setting aside the impossibility of such a scenario, you'd need to specify something like Earth, Solar System, Orion Spur, Milky Way Galaxy, Local Group, Virgo Supercluster, Laniakea Supercluster, Observable Universe. Each level zooms out by roughly a factor of 10 to 100, like those old educational films that started with a picnic blanket and pulled back to show Earth, then the Solar System, then the Galaxy, each transition expanding the scale by orders of magnitude. The experience of comprehending Laniakea is disorienting. We've gone from lying on grass looking up at a band of light to contemplating a structure that contains 100,000 galaxies, each containing billions of stars, each star potentially hosting planets, some fraction of which might harbour life that is also looking up, also wondering, also trying to make sense of the incomprehensible vastness that surrounds it. Beyond Laniakea, beyond all the superclusters, beyond any structure we've named or mapped, the universe reveals itself as a cosmic web. This is the largest pattern in existence, a network of galaxies stretching across billions of light-years, organised into filaments and walls and nodes with vast empty voids between them. If you could somehow see the universe from outside, a physical impossibility but imagination costs nothing, it would look like a three-dimensional spiderweb. Dense clusters of galaxies form the nodes where multiple filaments meet. Long, thin filaments of galaxies connect these nodes, tracing paths through space like threads connecting knots. Sheet-like walls of galaxies separate enormous voids, regions of space so empty that they contain almost nothing, sometimes spanning hundreds of millions of light-years without a single galaxy to break the darkness. The cosmic web emerged from tiny irregularities in the early universe. Shortly after the Big Bang, the distribution of matter was almost but not perfectly uniform. Some regions had slightly more density than others, mere fluctuations of perhaps 1 part in 100,000. but gravity amplified these small differences over billions of years, pulling matter from less dense regions into denser ones, forming the filaments and clusters we see today, while leaving the voids increasingly empty. Dark matter played a crucial role in this process. Because dark matter doesn't interact with light, it could begin clumping together immediately after the Big Bang, unimpeded by the radiation pressure that kept ordinary matter from collapsing. The dark matter formed a scaffolding, a framework of gravitational wells into which ordinary matter later fell. The cosmic web we observe today traces the underlying distribution of dark matter, visible galaxies like light strung along invisible cables. The filaments themselves are mind-bogglingly large. The Sloan Great Wall, one of the largest known structures, stretches about 1.38 billion light-years in length. Think about that. A single structure so vast that light needs 1.38 billion years to cross it. The observable universe is about 93 billion light-years in diameter, so the Sloan Great Wall stretches across roughly 1.5% of the entire visible cosmos. That might not sound impressive in percentage terms, but in absolute size it exceeds comprehension. Equally striking are the voids. The Buter's void, discovered in 1981, is a roughly spherical region about 330 million light-years in diameter, containing almost no galaxies. To put that in perspective, you could fit the Milky Way into the Buter's void more than 1 million times, with room to spare, and encounter almost nothing. It's sometimes called the Great Nothing, a region so empty that some have speculated, not entirely seriously, that it might be the result of advanced civilizations harvesting all the matter. Scientists still argue about whether the cosmic web is the largest structure in the universe, or whether larger patterns exist. Some analyses suggest that the observable universe, on the larger scales, is genuinely homogeneous. The same in every direction, with no structures bigger than about 1 billion light-years. Others have identified apparent patterns that might indicate structures spanning significant fractions of the observable universe. The data is inconclusive, and the philosophical stakes are high. If the universe looks different in different directions, some of our most fundamental cosmological assumptions would need revision. Here's a quirky visualization. Imagine you're a bacterium living on a strand of a spider web. You can crawl along your strand, and you can see other strands nearby, but you have no idea how big the web is or what shape it takes. That's humanity's position in the cosmic web. We live on one small node of one filament, able to map our local region, but only dimly perceiving the vast architecture that extends in all directions to the edge of observability and presumably beyond. The Milky Way is one point in this network, one small galaxy and one small filament on the outskirts of one supercluster. When you look up at the stars, you're seeing the tiniest fraction of your immediate cosmic neighborhood, which is itself an infinitesimal piece of a structure that spans the entire observable universe. Let's slow down now, let's breathe, let's follow a single photon on its journey through the cosmos. It's a humbling exercise, tracing the path of light from its creation deep inside a star to its eventual encounter with your eye or a telescope or the void between galaxies. Light travels at 186,000 miles per second, the fastest anything can go, the cosmic speed limit, and yet even at this unimaginable velocity, crossing the Milky Way takes a very long time. Inside the Sun's core, where temperatures exceed 15 million degrees and hydrogen atoms fuse into helium, a photon is created. This photon doesn't travel in a straight line. The plasma inside the Sun is so dense that the photon immediately collides with an atom, is absorbed, re-emitted in a random direction, absorbed again, re-emitted again. This process repeats countless times, the photon bouncing around in a random walk that takes, on average, about 100,000 years to traverse from the core to the Sun's surface. Think about that. A photon of light, moving at the fastest possible speed, needs 100,000 years just to escape the star that created it. Most of that time is spent not moving at all, waiting to be absorbed and re-emitted, making almost no progress toward the surface. The photon that will eventually reach your eye tonight might have begun its journey when Neanderthals still walked the Earth, finally breaking free of the sun's surface only to face the 8-minute sprint across interplanetary space to your retina. 8 minutes is nothing cosmically speaking. Light from the moon reaches you in about 1.3 seconds. Light from Mars at its closest takes about 3 minutes. The outer planets take longer. Neptune is about 4 hours away at light speed. But these are still trivial distances compared to interstellar scales. The nearest star to the Sun, Proxima Centauri, is about 4.24 light-years away. That means the light you see from Proxima tonight left that star 4.24 years ago. If Proxima exploded tomorrow, we wouldn't know about it until 2030. And Proxima is our nearest neighbour, the closest star in the entire galaxy. Most stars in the Milky Way are vastly farther away. A photon from a star on the far side of the galaxy, if it could travel in a straight line without being absorbed by interstellar dust, would take at least 100,000 years to reach us. More likely, it would be absorbed by dust along the way, its energy converted to heat, its journey ended prematurely. The photons that do reach us from distant parts of the galaxy have taken winding paths, finding the gaps between dust clouds, navigating a cosmos that is only mostly transparent. Scientists still argue about exactly how much of the galaxy's light reaches us. Interstellar extinction, the dimming and reddening caused by dust, varies dramatically depending on the direction you look. Toward the galactic centre, extinction is so severe that visible light barely penetrates at all. We have to use infrared and radio wavelengths to peer through the murk and see the crowded stellar populations near Sagittarius, a star. Here's a quirky fact. When you look at the night sky, you're looking at the past. The stars you see are not where they appear to be now. They're where they were years or decades or centuries ago, and the light has been travelling ever since. If you could somehow see the Milky Way as it is now, in some absolute objective sense, you'd see a completely different arrangement, stars shifted by their proper motions, some that appeared stable having exploded into supernova, others having formed from nebulae that didn't yet exist in the light you're currently seeing. The universe is a time machine, showing us different epochs depending on how far we look. Nearby galaxies show us the universe millions of years ago. Distant galaxies show us the universe billions of years ago. The cosmic microwave background, the oldest light we can detect, shows us the universe as it was 380,000 years after the Big Bang, a baby cosmos barely recognizable as the progenitor of today's web of galaxies. You can feel your eyes growing heavy again, your thoughts softening at the edges, the journey of photons becoming a kind of meditation. Light travels across the cosmos, patient and unhurried, carrying information about stars that may no longer exist to eyes that couldn't have been predicted when the journey began. There's something beautiful about that, something worth holding on to as you drift. We've talked about the Milky Way, about its neighbours, about the superclusters and filaments that structure the cosmos. But now we need to confront the final, most humbling truth, the observable universe itself, and how small our galaxy is within it. The observable universe is about 93 billion light-years in diameter. This number is larger than you might expect, given that the universe is only about 13.8 billion years old. Shouldn't we only be able to see 13.8 billion light-years in any direction? The answer involves the expansion of space itself. Light from the early universe has been travelling toward us for 13.8 billion years, but the space it has crossed has been expanding behind it, so the objects we see in the oldest light are now much farther away than they were when the light left them. Within this observable universe, there are approximately 2 trillion galaxies. 2 trillion. That's 2,000 billion, 12 zeros, a number so large it loses all meaning when you try to visualize it. Each of these galaxies contains billions of stars. The Milky Way's 400 billion stars, which seemed so incomprehensibly numerous just a little while ago, represent roughly 0.00002% of the total stellar population of the observable universe. Let's try some comparisons. If the Milky Way were a single grain of sand, the observable universe would contain 2 trillion grains. That's roughly the number of sand grains on all the beaches of Earth. We are 1 grain of sand on an infinite beach, looking up at a sky full of other grains, each one a galaxy in its own right. Or try this. If you could shrink the Milky Way to the size of a dinner plate, the observable universe would be about the size of the continental United States, our entire galaxy. All 400 billion stars, all the planets and nebulae and dark matter would fit on your kitchen table, while the universe spreads from coast to coast. The numbers resist comprehension. Human minds evolved to understand quantities relevant to survival: how many predators, how much food, how far to walk. We have no intuitive capacity for trillions. We can say the words, we can write the numbers, but we cannot feel them the way we feel 10 or 100. Scientists still argue about what lies beyond the observable universe. We can only see objects whose light has had time to reach us since the Big Bang. Beyond the cosmic horizon, more universe presumably exists, possibly identical in character to what we can see, possibly different, possibly infinite, possibly finite but unbounded like the surface of a sphere. We may never know. The expansion of the universe is accelerating, which means objects beyond a certain distance are receding faster than light and will never be visible to us no matter how long we wait. Here's a quirky thought experiment. If there are 2 trillion galaxies in the observable universe and intelligent civilizations are rare but not impossible, how many might exist? Even if only 1 in a million galaxies hosts intelligent life, that would be 2 million civilizations out there, looking up at their own night skies, wondering if they're alone. And 1 in a million is probably conservative. The conditions for life might be more common than that. We have no way of knowing, no way of detecting these hypothetical neighbours across intergalactic distances, but the statistical argument for their existence is compelling. The Milky Way floats in this ocean of galaxies like a single leaf on an endless sea. It's where we come from, the only galaxy we know intimately, the home that has nurtured our sun and planet for 4.6 billion years. But it's not special, not at the centre of anything, not particularly large or small, not marked by any cosmic significance that would distinguish it from the trillions of others. We're ordinary, magnificently, beautifully, humblingly ordinary. What lies beyond? This is the question that haunts cosmology, the edge where science shades into philosophy, where observation reaches its limits and speculation takes over. Beyond the observable universe, beyond that 93 billion light-year sphere we can see, there is almost certainly more. The universe didn't stop at the edge of what our telescopes can reach. That edge is an accident of light travel time and cosmic expansion, not a physical boundary. Most cosmologists believe the universe extends far beyond what we can observe, perhaps infinitely, perhaps merely vastly. But believe is doing a lot of work in that sentence. We have no way to test what lies beyond the cosmic horizon. Light from those regions will never reach us, no matter how advanced our technology becomes. The expansion of space is carrying those distant regions away faster than light can travel toward us, creating an informational barrier as absolute as any physical wall. The simplest hypothesis is that the universe beyond the horizon looks much like the universe we can see. More galaxies, more superclusters, more cosmic web stretching on and on. This is a reasonable inference from what we know. The universe appears homogeneous on large scales, roughly the same in every direction. So why would it suddenly become different beyond our vision? But there are other possibilities. Some theoretical physicists argue for a multiverse, a vast or infinite collection of universes with different properties, of which our observable cosmos is just one bubble. In some versions of this idea, the laws of physics vary from universe to universe. In others, the laws are the same, but the initial conditions differ. We have no way to test these theories directly. They remain mathematically motivated possibilities rather than scientific conclusions. Eternal inflation is one framework that leads to multiverse predictions. if the inflationary period that briefly expanded the early universe never fully stopped, if inflation continues forever in some regions while stopping in others, then bubble universes would constantly form, each one potentially developing into a cosmos like our own. Our observable universe would be one such bubble, surrounded by an eternally inflating sea that spawns bubble after bubble forever. Scientists still argue fiercely about whether multiverse theories count as science at all. If they make no testable predictions, are they physics or philosophy? Some argue that indirect evidence, cosmological signatures of bubble collisions for instance, might someday confirm or refute these ideas. Others maintain that unfalsifiable theories, however mathematically elegant, belong in the realm of speculation rather than science. Here's a quirky fact. Some calculations suggest that in an infinite universe, with truly random initial conditions, exact copies of you would exist at unimaginably large but finite distances. If the universe is infinite and matter is arranged randomly, then any finite pattern, including the precise arrangement of atoms that constitutes your body and brain, would eventually be repeated by sheer chance. These hypothetical doubles are so far away that light could never travel between you, but mathematically speaking, they would exist. This is known as the Boltzmann brain problem, and it causes headaches for cosmologists trying to make sense of infinity. You lie there in the grass feeling suddenly very present, very singular, very much yourself despite the mathematical possibility of infinite copies. The universe may extend forever in all directions, spawning galaxies and stars and possibly even versions of you. But this moment is unique. This grass beneath you, this sky above you, this specific arrangement of neurons contemplating the infinite, this is yours, and yours alone, even if 1 trillion copies are having the same thought in distant pockets of an unimaginably vast cosmos. The edge of the observable universe isn't the edge of reality. It's just the edge of what we can know. Beyond it, mystery continues, perhaps forever. And so we return to where we started. You, lying on cool grass looking up at the Milky Way. But the band of light means something different now. It's no longer just a smudge across the sky. It's a structure containing hundreds of billions of stars, one of which is your sun, orbiting in the quiet suburbs of a spiral galaxy that's hurtling toward a collision with its nearest large neighbour, which is itself just one member of a local group embedded in a supercluster called Laniakea, which is itself a small knot in the cosmic web that structures an observable universe containing 2 trillion galaxies, which is itself possibly just a bubble in an infinite multiverse stretching beyond the reach of light or knowledge. That's a lot to hold. You don't have to hold it all. The sky above you is unchanged. The stars haven't moved in any perceptible way since you first stepped outside tonight. The Milky Way still glows with the same soft luminescence that your ancestors saw 50,000 years ago, that Galileo saw through his imperfect telescope, that William Herschel tried to map by counting individual points of light until his eyes ached. The universe is vast beyond comprehension, but this view, this particular view from this particular planet, has been a constant companion to every human being who has ever looked up. There's comfort in that. The same stars that shine tonight shone over ancient Egypt, over Renaissance Italy, over your grandparents as children, over you as a child. They'll shine over your descendants, assuming humanity persists for millions of years to come. The individual stars will change, some will die, others will be born, but the Milky Way itself will endure, transforming slowly through collisions and star formation and the patient work of gravity, but recognizably present as long as there are eyes to see it. The scale is terrifying, yes. You're small beyond imagination, a mote on a mote in an ocean of space and time, but you are also remarkable. You are matter that knows it is matter, energy that has organized itself into a form capable of looking back at the universe and asking questions. In all that vastness, in all those 2 trillion galaxies, we don't know of any other being doing what you're doing right now. lying in the grass, contemplating infinity, feeling both the terror and the beauty of the cosmic scale. Maybe there are others. Probably there are others, given the numbers involved. But we don't know where they are or what they think, or whether they look up at their own night skies and feel the same mixture of awe and insignificance that you're feeling now. For the moment, you're alone with your thoughts under the stars, and that's okay. Being alone doesn't mean being unimportant. The Milky Way is your home. Not Earth specifically, that's your address. But the galaxy itself is the larger neighbourhood where you were born, where the atoms in your body were forged in ancient stellar furnaces, where life emerged and evolved and eventually became curious enough to ask the questions we've been exploring tonight. Here's one last quirky fact to carry with you into sleep. The atoms in your body are ancient. Some of the hydrogen has existed since the Big Bang, 13.8 billion years old. The heavier elements, the carbon in your cells, the calcium in your bones, the iron in your blood, were created inside stars that lived and died before the sun was born. You're made of stellar ash, recycled matter that has passed through multiple generations of cosmic furnaces to arrive at this particular configuration, on this particular night, under these particular stars. Scientists still argue about many of the details we've covered tonight: the exact size of the Milky Way, the nature of dark matter, the boundaries of Laniakea, the existence of other universes. These debates will continue, and the answers we have now will likely be revised as our instruments improve and our understanding deepens. But the basic truth won't change. We live in a galaxy that is staggeringly large by human standards and infinitesimally small by cosmic ones, and somehow we've developed the capacity to know this about ourselves. Let that knowledge settle into you like warmth spreading through tired muscles, and now let the numbers drift away. Let the light years and the billions dissolve into soft abstraction, no longer demanding your attention or your comprehension. The Milky Way continues its slow rotation above you, as it has for billions of years, as it will for billions more, patient and indifferent and beautiful in the way that vastness is always beautiful when you stop trying to measure it. Your eyelids can fall now, heavy with the effort of imagining distances that weren't meant for human minds. The grass beneath you has become a bed, the night air a blanket, and the distant stars a kind of lullaby. Not in any sound they make, but in their constancy, their presence, their willingness to shine whether anyone watches or not. You are part of this. Not a visitor, not an observer, but a genuine constituent of the cosmos, made from the same stuff as the stars, subject to the same gravity, bound by the same physical laws. The universe didn't create you by accident and isn't keeping you around by negligence. You emerged from it, as natural as a wave from the ocean, and one day you'll return to it, your atoms scattering to become part of something else entirely. But not tonight. Tonight you rest, cradled by a planet that has circled its star more than 4 billion times, orbiting within a galaxy that has made about 20 circuits of its own vast centre. The scale doesn't matter now. What matters is the breath entering your lungs, the softness beneath your body, the quiet settling of your thoughts into peaceful darkness. The Milky Way will be there when you wake. The universe will still be vast, and you will still be part of it. Small, yes, but present, aware, and wonderfully, improbably alive. Sleep now. The stars will keep watch.